Hi everyone and welcome back to Physics 2A. Hopefully you guys were okay with the exam last week, and hopefully we can move forward from that. So today I wanted to talk to you guys about uniform circular motion and gravitation. Okay, so we're going to start with rotation. Let's see, uniform circular motion is going to be a motion in any kind of circular path with a constant speed. Okay, so notice that doesn't say velocity, okay, because our velocity is going to be changing throughout that circle. And that is because the direction is changing. Okay, so if I have a circle that I'm moving throughout, okay, and I'm constantly moving 0.1, 0.2, 0.3, okay, my speed, or V, is going to be constant. Oops. But as you notice, my direction is changing. Okay, so that is what is going to be different here when we're talking about rotation. Okay, and to describe this rotational motion, we're going to need to know two main quantities, and that is going to be the rotation angle and the angular velocity. Okay, so I'm going to go into each of those. The rotation angle is going to be my delta theta here. That's how it's going to be represented. And that is going to be the ratio of the arc length, this delta S here, okay, to the radius of curvature, which is just the radius of the circle, okay, if we're going in a circular motion, right? So that's how we define our rotation angle, okay, this rotation angle here, okay. Note that for one complete revolution, so if I start from point A and I travel all the way around this circle and end up back at point A, I want to know how far I've traveled. Well, I can use this delta theta here to figure that out, okay. So if we think about it, delta S in that case, okay, is the same as the circumference of a circle. Remember that a circumference of a circle is 2 pi r, okay? So that's what we plug in here as our delta S, okay? And then we divide it by our radius again, which is just r. So for any circle, okay, for any circle, it doesn't matter what the radius is, my, for one complete revolution, my rotation angle is 2 pi, okay? Now, I also want to mention the units of this rotation angle is typically in radians, okay? And so when I say 2 pi, I mean 2 pi radians, okay? And again, hopefully you have gone over this in some other math class, but if not, that's okay. Just know that this entire circle, that's also 360 degrees, okay? So we know that 360 degrees is the same thing as saying 2 pi radians, okay? And this can be used throughout learning in this section because we may have to translate from radians to degrees or vice versa, okay? So we just want to watch out for that, okay, when we're doing this, okay? So that is rotation angle. Then we have angular velocity, okay? And velocity, remember, is some kind of rate of change, right? And so instead of having as like a regular velocity, we have some kind of delta x over delta t, right? We have some change in position over a change in time. Now we have a change in that angle that we just talked about, that rotation angle, over some change in time, okay? So notice the similarity to these two, okay? That change in position is like the change in the angle, okay, over time. And we can actually look at both of these and kind of compare them, okay? So we have this relationship here between angular and linear velocity, that's what we would call this. This v would be linear, right? Because it's not rotational. Okay. And so we can say that omega, that's what that little w looks like. It's actually called an omega, equals my linear velocity over some radius. Okay. So take, for example, this car here, and we've got some tire and wheel. Okay. And it's moving. Okay. So we have some kind of rotational velocity here, this omega. Okay. And then we also have the velocity of the car. Okay, now this velocity of the car is also going to be this linear velocity. Okay, so we want to really know how to relate all of these things in order to figure out different velocities, and maybe we need to find the radius, or maybe we need to find that angular velocity. Okay, so we want to know this relationship. And so this is an example of a good way to kind of understand it, a good way to use it in practice. Okay. I also wanted to point out that a large linear velocity, so a large v, if this value goes up, okay, that means that it has a large omega. Okay. So think about that for a second. If I increase my velocity here, so if I move this car faster, okay, if I push on the gas more, that linear velocity is going to go up, right? So if I went from 30 miles an hour to 50 miles per hour, right? My linear velocity is going up. That means my rotational velocity, or my angular velocity, sorry, my angular velocity will need to increase, right, in order to get my wheels moving faster. Okay, so that makes sense. I also have that a large radius means a large linear speed. Okay, so if I have a radius that is large, okay, and I switch around this equation like it has here, okay, if I increase my radius, okay, that means my linear speed is going to increase as well. Okay, so this is just something I wanted to point out to you guys, and go on from there. So we also need to talk about acceleration in this angular sense, okay? Because if we can talk about our acceleration, then we can talk about our forces, okay? So our centripetal acceleration is going to be a motion. I'm sorry, our centripetal acceleration is going to be where we have some kind of constantly changing velocity. Remember I said that the velocity is going to be constantly changing because that direction is changing, okay? And such that, sorry, my dog is distracting me, such that my or I will always have acceleration, right? So if I have a delta V, I will have some acceleration, okay? But if my delta V is 0, that means no acceleration, right? Okay, so with this motion, in this uniform circular motion, we will always have some kind of acceleration, and we call that centripetal acceleration, okay? And we want to note that our acceleration is always going to point in the direction of the change in velocity, okay? So what does that mean? Take this case for instance, okay? So we have 3 different points, okay? And we have 2 velocities that we took, say, okay? And we put them together in this little graph. Say this is an XY graph, for example. So we translated this onto here, and we said V and V2. We want to know that change in velocity, okay? So that's going to be V2 minus V1, okay? That change in velocity. And so that change in velocity as you can see, is pointing in this direction, which is actually towards the center of our little circle here, right? Or we can call this the center of mass, okay? That's the point at which it's the center of the mass, if that kind of makes sense. I'll get to that in a second too. So again, our change in velocity points to the center of our system here, okay? So we know that at any point now, the acceleration is always going to point inwards, okay, towards that center. All right, and we do have an equation here for this. Our acceleration, and we put a little c here so that we know it's centripetal acceleration, okay, is our velocity squared over our radius, or our radius times omega squared, okay? And you can relate that back from this equation here, okay? So just remember that these all connect, all right? Okay, so moving on from centripetal acceleration, we can now look at our centripetal force, okay? And again, we say that this is F sub c, okay? And we would calculate it the same way that we would calculate a regular force. So our force from Newton's second law is mass times acceleration, right? So we're gonna do the exact same thing, but now our acceleration, whoops, mass times acceleration is our centripetal acceleration, okay? So we'll have to make sure that we put that little c there, and we can plug in from there. Okay, so I can continue from here and plug in my centripetal accelerations to get two different forms depending on what I'm looking for or what I already have, okay? So one thing that I should point out, kind of looking at this, that our forces in the past are always in the same direction as our acceleration, right? Because they're linearly related, right? So our force is in the same direction as our acceleration. Okay, so that's no different here. So our centripetal force is going to be in the same direction as our acceleration, or our centripetal acceleration, okay? So just wanted to point that out, okay? So here is my arrow that is our force, our centripetal force here, okay? Then we have our radial vector, which is just our distance here, okay? Then we have our velocity vector, which is always going to be tangential, or we can say perpendicular to our force here, okay? See how it's perpendicular at 90 degrees at whatever point we're looking at, okay? So these are just things to note, okay? We can also rearrange some of these equations. Say we're solving for our radius, we can do that, okay? Yeah, that's pretty much all I wanted to talk about with centripetal force. Now I wanted to mention some forces that are fictitious. Okay, so these are things that people tend to talk about when they talk about, they're trying to talk about centripetal forces. Okay, so these fictitious forces, have no physical origin. Okay, so this means that we're just kind of claiming that it's some kind of force. Okay, and what am I talking about? So let me give you an example, and this is something that we should pretty much have all felt before. You're driving in a car, okay? So say you're driving in a car and you're turning to the right, just like this car is. See how the wheels are that way? So they're trying to turn right, okay? So when I'm turning right, I am applying a force in that direction. See how it says F actual? That's my force that is being applied, okay? Now, we feel like we're going in the opposite direction, right? When we're in the car, we feel like we're going this way, like this fictitious force says right here. And so that's what we call this fictitious force, okay? It's like we're being pushed in that opposite direction, but we're really not, right? It's all about what we talked about last time, Newton's third law: for every action, there's an equal and opposite reaction. Okay, that's all it is. There's no other force that's being added. Okay, it's just that's just what we feel like we're getting some other force, but we're not. Okay, so I just wanted to mention these. There's also the centrifugal force, which I have here. Again, it's very similar. It's you're going in a circle, so it's like a centripetal. There should be a centripetal force, okay, involved here, and that's the one that's here, going in towards the center. But when we're going around in, say, this merry-go-round, we feel like we're being pushed out this way, okay? Again, it's all about Newton's third law, okay? So just be careful when you're talking, I guess, and thinking about this stuff. So these are fictitious forces, okay? All right, there's also the Coriolis force, which I'm not gonna go into, just wanted to mention it, okay? Your book does go into more depth with it. All right, so this would probably be a good spot to break. So if you wanted to go ahead and do so, I would recommend it, okay? But I'm gonna go ahead and move on. So Newton's universal law of gravitation, okay? This is what is pretty important, okay? In physics at least. So for every particle in the universe, okay, every particle in the universe either has some kind of attraction between them, okay? So if we have one particle here and another particle here, there is some kind of attraction between them. And that's not just, you know, when we're talking about like chemistry, we're not talking about like, I mean, we could probably talk about the molecular, get into that depth, but what I'm really talking about is everything, okay? I'm talking about a calculator to my table. I'm talking about, you know, me on the earth, okay? So it's these two objects that have some kind of force that attracts them, okay? And this force is proportional to a gravitational constant, which I have here, and their masses, okay? The masses between the two, okay? And the radius that separates them, okay? So in this case here, we have two, we'll just say objects or particles, okay, with some center of mass. That's what this is. So center of mass, like I talked about before briefly. Okay, so that's where the mass is concentrated, I would say, or like the average center of the mass, okay? So we have two of those. They're separated by some distance or radius r, okay? And they have two different masses, okay? Little m and big M, okay? So this equation here will describe the force that attracts these two objects, okay? So this force equals my gravitational constant times a little m, or little mass, times a large mass over my radius squared, okay? And this gravitational constant I gave here as 6.674 times 10 to the negative 11 Newton meters squared over kilograms squared. Okay, so it's just a constant, and this is actually universal. Okay, so it's not like our own acceleration due to gravity on Earth, little g. Okay, so don't confuse that with big G. Those are very different. Okay, but we can use this formula now to solve for our acceleration due to gravity. And we can do that for Earth, we can do that for the sun, we can do that for pretty much anything now, okay? So let me show you how, okay? So we know that F equals big G, little m, big M over r squared, okay? We also know that force is some mass times an acceleration, okay? And our acceleration that we want to know is gravity on Earth, okay? And we can substitute this for, you know, gravity on another planet, on another moon, maybe on the sun if we get crazy. I know we're not going to the sun anytime soon, like us personally, but you know, it's something that we can calculate, okay? So if I want to solve for G on Earth, I'll just write a little Earth right there, okay? I can set this equal to each other because my force is equal to this and it's equal to this, okay? So from that, I can find that G Earth, gravitational acceleration on Earth, okay, is equal to, my little masses cancel, and I get my gravitational constant times my big mass over r squared. Okay, now let me kind of give you guys an idea of what the M's are standing for in this sense. So when I'm looking at this force, this mass times gravitational acceleration, okay, sorry, my dog again. This mass, if I'm looking at, say, me, it would be me. So the mass of me. This force here is like a weight. If you remember from last time, right? This force due to gravity is like some kind of weight. Okay. So that's what I mean when I'm talking about this little m. It would be the mass of whatever object it is. And in this case, when we're trying to figure out the overall gravity or acceleration due to gravity, it cancels out anyway, it doesn't really matter. So then what is that big M? That big M would then be the planet you're looking at, the moon you're looking at, the sun, okay? So whatever those masses are, okay? All right, so moving on from there, I just wanted to briefly mention how tides on Earth are caused, or what they're caused by. And they're caused by moon's gravity and the gravity that's acting on Earth. Okay, so let's look at this illustration here. It's from your textbook. I think it's a little bit better. I think it's easier to look at than this one. So of course, this is not to scale, thank you. We have Earth here and we are rotating this direction. That's what it's stating. Okay, and then the moon is moving this direction. Okay, so this here would then be my omega. And then this is some kind of velocity, right? Tangential velocity of the moon. Okay, so we have the Earth that is rotating here. We have the moon that's orbiting us, okay? And so the gravitational pull between the two, okay, we have some kind of centripetal force, right? Or we have, I'm sorry, not centripetal force, gravitational force. I know my brain is slowing down. So my gravitational force here, okay? And because of this, okay, because of this attraction, we are, or sorry, not we, but the moon is pulling at the waters, or our tides, okay, and then creating high tides and low tides. Okay, so as you can see, the high tides are going to be towards and away from the moon. The low tides are on the other sides of Earth. Okay, so we get 2 high tides per day. Okay, just a little bit of information. I just wanted to kind of give you a brief understanding about that. Anyway, moving on. Now we want to look at Kepler's 3 laws. Okay, so the first one basically is stating that all of our planets are moving in ellipses around the sun. Okay, so here we have that illustration. We have some planet here and it's moving around the sun. Okay, and that the sun will be at some kind of focal point, either focal point 1 or 2. Okay. Now, what do I mean by focal point? An ellipse is kind of a funny shape. Hopefully, or maybe you guys have taken geometry in the past. And an ellipse is just a circle with two focal points. Okay, so it's kind of like a stretched out circle, like an oval or maybe like an egg shape. Okay, that's what an ellipse is. I tend to think of it as like, what the heck? I did not draw that, I swear. Let me erase that real quick. Okay. As like two circles with two focal points and then kind of like circled in both of them. Okay, I know that's really ugly, but it gets the point across. Okay. We also say in math that it's a closed curve, so that the sum of these two distances, distance 1 and distance 2, okay, sorry, the sum of the two distances from a point on the curve is constant. Right. So this distance and this distance added up is going to be the same no matter where you draw that point on the ellipse. Okay, so these distances are always going to add up to equal the same thing. That's all it's saying. Okay. So again, going back, Kepler's first law, all it's really saying is that the planets move in an ellipse around the sun. Okay, that's the main idea I want you guys to get out of that. Okay, now Kepler's second law is a little bit more in depth with that. Okay, so again, we have our planet moving in an ellipse around our sun. Okay, and it's saying that as this planet moves around, the area that it sweeps out, aka it goes from here to here, from A to B, this little area that it makes with the sun here, A1, is going to equal the same area that it sweeps out from two other points in that ellipse course or path. Okay, so A1 is going to equal A2. Okay, and as it goes along, it'll even be the same as here, A3. Okay, so A1 equals A2 equals A3. All these areas are the same. Okay, and it also sweeps those out in equal times. Okay, so the time for the planet to move from A to B, say T1, is the same amount of time that it takes for the planet to move from C to D, T2, and so forth, T3. Okay, so what this means, if you just look at this and kind of think a little, okay, we're following this planet and it gets from A to B and it's going some kind of speed. From C to D, do you think it's going faster now or slower now? If it has to travel some distance, right, some like arc here, here and here, is it having to go faster or slower from A to B to D to C? What do you think? It is going to have to slow down now, right? Okay, so in this first section, it's going to be going some velocity, v1, okay, here. And as it moves this way, it has a smaller distance to travel, right? So it's going to be slower here from C to D. Okay, so this V1 is going to be faster than V2. And it's going to be, this last one here is going to be even slower than V2. Whoops. There we go. Because it has such a short section to cover. Okay. And again, when we think about gravity, okay, think of it this way. I'm sorry, my dog needs to be let down. Okay. All right. So what was I saying? I was saying thinking about gravity, right. So gravity here, we have a greater force due to gravity since we're at a smaller radius here, right? So hold on, let me erase some of the pen real quick. It's getting kind of messy. So say we are here at A, okay? We are at some radius from the center of mass, right, in the sun. We are at some radius, okay? And then if we're looking way over here on this other side, from F to the center of mass of the sun, we have some other radius, okay? So which radius is larger? This one, right? So here, R1 is less than R2. Okay, so if I am thinking about the universal law of gravitation, so F equals G little m big M over R squared. Whoops, R squared, not 2. Okay, and I'm comparing these two forces here. Okay, this one, let's just say that's 1, and then this one's 2. Okay, if I'm comparing the two, okay, so F1 over F2, okay, this would give me 1 over, let's see, 1 over 2 squared. Okay, so this is like 1 over 1/4, or we can say that F2 is going to be 4 times the amount of F1. Okay, because if we flip it over, right, that's just equal to 4. Okay, so F1, or I'm sorry, yeah, F1 is going to be 4 times the amount of F2. Okay, so we have a larger gravitational force here than here. Okay, so F1 is larger than F2. So if I have a large gravitational force, okay, it'll like speed up through here, okay, and then it'll slow back down. Okay, so that's how this will look when we are looking at orbits of planets. Okay. Okay, so moving on to Kepler's third law. Okay, this is sort of related to what I was just talking about, but now we're looking at the periods. The periods is just T, okay? That's at T here. And if we're comparing two planets, I should first go over this one. So, okay, so T is the period, right? That's here, or the time for one orbit, and R is the average radius, okay? We have G, our gravitational constant, and then M is the mass of whatever we're looking at, okay? And Kepler's third law states that if we compare two objects that are going around the same thing, say the sun, okay, we can write this ratio as such, okay? So think about if we did T1 squared divided by T2 squared, and it would be like 4 pi squared R1 to the cubed over G M and so forth, R2 cubed. These constants would cross out and we'd be left with this ratio. Okay, so that's all Kepler's third law is stating. Okay, and I wanted to leave you with another way of kind of looking at this formula here. And that is when we want to determine something like the mass of that parent body. So like if we wanted to know the mass of the sun, for instance, or the mass of Earth, given something, blah, 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 okay. it'd be something like that. If we knew something about the orbits of its satellites, okay? AKA, if we knew something about Earth, we can determine the mass of the sun. If we knew about something about the moon, we can determine the mass of the sun. Okay, so that's kind of what we're looking at here. And you can look at table 6.2 in your textbook for a little bit more information on that, more information on these ratios and such in order to use this whole equation. Okay, and that will be in the homework, so kind of watch out for that. But hopefully I can get through some examples. I don't know if I have an example on this, but if you have any questions, of course, you can email me. All right, and that is it for this lecture. I will go ahead and post some more stuff on, whoops, discard, post some more stuff on Canvas about your lab and your homework and such, okay? All right, until next time.